the commutator of x comma h, where potential energy is a function of x, y, z alone. Okay, what is the answer for this question? Right, listen, first you take the commutator which is present inside. Okay, let me work out that first. X comma h bar equal to, what is x comma h bar? See here, you keep this, x is an position operator, and the Hamiltonian operator can be written as kinetic energy operator plus potential energy operator. Okay, Hamiltonian is nothing but kinetic energy plus potential energy. Therefore, I can separate this into two according to the commutation rule, right? So you can write this as x comma t and x comma v. You can write this in two operators. Okay, x comma t can be written as, I'll keep x as such, kinetic energy operator. What is kinetic energy? Minus h bar square by 2m into d square by dx square. Okay, I'll take one dimension here because we have only x, so y and z automatically become 0, plus here potential energy is a function of x, y, z. Okay, it's a function of position only. Therefore, these two x comma v commute, so you will get the commutator of this value is 0. Okay, x v will commute and the value is 0. Then you know very well the commutator formula, if you use, you will get the same answer. Okay, that is ab minus ba should give same answer for x comma v, therefore the answer is 0. Whereas here we have to find out the result. Okay, so how to do that? You know very well this operator can also be written as x comma kinetic energy operator can also be written as px square by 2m. Okay, this you can also write like this, where px square is the linear momentum operator. Okay, see 1 by 2m is a constant, so you can keep it out. Right, so what we left, x comma px square. Right, x comma px square can be written as, okay, this is position, this is momentum. Okay, position, but momentum square is there. Therefore, the value of this commutator is I h bar. Okay, you know very well, position momentum commutator value is I h bar. So I h bar, and we have square is there. Therefore, 2 into px power 2 minus 1, that is 1. Okay, this 2 and this 2 you can cancel. So we get I h bar by m into px operator. Okay, so you just go through the options. If you go through the option, the first option is I h bar, second option minus I h bar, third option minus h bar square by 2 by m, and in fourth option we have I h bar m by px operator. So this is the value of x h bar. I'm sorry, the problem is not yet finished. We have one more, right? Okay, we have completed this. Now we have to consider the whole commutator. So what is the whole commutator? The whole commutator is x comma x plus x comma h bar. This is the question that is asked. Now I'll keep this x as such, and what is the value of this commutator? We found that it is I h bar by m into px operator. Okay, we found the value of x comma h bar commutator, and the value of the commutator is this. So in the place of x comma h bar commutator, I'll put this value. Okay, I h bar m is constant, so you can keep it out. You can keep it out. So what we left with is x comma px operator. position and momentum do not commute, and you know the value is, I'll keep this IH bar m as such, the value of this is IH bar. So here I have IH bar, here I have IH bar, I into I square is minus, so minus H bar square by m. So this is the correct option for this question. So this is the answer for this question. So what's the correct option? See, option A, option B, option C, yes, minus H bar square by m. So the correct answer for this question is option C. Okay, students, is this clear? Any doubt here? You just go through this, and if you find any difficulty, you tell me. We found this value and I have substituted in the place of x comma h bar here. Okay. You know very well, right? Here I think we discussed this formula anyway. Listen, under commutator you should remember these points. That is, if you have a commutator of two operator AB, commutator is nothing but AB minus BA. Okay, this is we know. And commutator of AB should be equal to minus the commutator of BA. This also we know. Okay, then the commutator of position and momentum, right, is IH bar. Okay, and the commutator of x power n into px operator is IH bar. You keep this IH bar as such. X power n is there, so n into x power n minus 1. Similarly, x comma px power n, suppose if you have power n here, then the answer for this commutator is IH bar into n into px power n minus 1. These are all formulas which are available in almost all books. So just remember these formulas. So what I did here, I used this formula, okay, and I found the value of the commutator. See here, I used this formula px square by 2m. I took 1 by 2m out, so we have x comma px square, and now the value of n is 2. Okay, so what is the commutator for this? It is nothing but IH bar. Keep IH bar as such, and apply the formula 2 into px power 2 minus 1. So 2 into px power 2 minus 1 is 1. Okay, so we got this answer for x comma h operator. This is the commutator for x comma h. Substitute that value here, and again apply the commutator for x comma px. You will get this answer. Okay, yeah. So this is question number 1. Right. So for the question number 1, the correct option is C. Right. Let me go to the next question. That is question number 2. Yeah. Students, go through the question and try to answer it. If you know the answer, just send it in the meet. Okay. A particle is confined in a cubical box of length L. If the energy of the particle is 51 h square by 8 ml square, then the degree of degeneracy associated with the energy level is. What is the degree of degeneracy associated with this energy level? Yes, students, can you do this calculation? Can you find the answer for this question? The value given is 51 and it is a cubical box. Right. You know very well, for particle in cubical box, okay, for a particle confined in a cubical box. The formula for energy depends on 3 quantum numbers. So the formula for energy is this, that is nx square plus ny square plus nz square times h square by 8ml square, where m is the mass of the particle and L is the side length of the box. Since it is cubical box, all side lengths are equal. Okay, this is the energy formula. Now the particle have at a particular state, it has an energy 51 h square by 8ml square. Okay, so let me equate that. Nx square plus ny square plus nz square into h square by 8ml square. This is the energy formula. This is equal to 51 times h square by 8ml square. So we can cancel this and this. Therefore, nx n square plus ny square plus nz square, this quantity should be equal to 51. Okay, this is possible by taking different set of quantum numbers nx, ny and nz. Right? I should get, if I square that, I will get the answer as 51. Okay, nx square plus ny square plus nz square value should be equal to 51. So what are the possible values? Okay, if anybody got the answer? Right, let me do this and give you the answer. Listen, the first combination is this. Okay, you take nx as 7, ny, nz as 1, 1. So this is 49, nx square is 49, ny 1 square is 1, 1 square is 1, so 49, 50, 51. Okay, I'll get 51 here. And here we have 3 combinations, 711 or 171 or 117. Okay, so degree of degeneracy can be 3, but whenever question given like this, you have to think other possibility also. Okay, we have one more possibility here. What is that? To get 51, I can take 5, 5, 1. 5 square is 25. 5 square 25, 25 plus 25 50, 50 plus 1 51. So this is also will give you 51, and here we have these possibilities 5 1 5, then 1 5 5. So all together we have 6 degenerate states. Okay, so this energy 51, okay, or the particle having energy 51 h square by 8ml square, this energy level has 6 degenerate states. Okay, I think there won't be any other states possible for 51. So the degree of degeneracy for this question is 6. Okay, for this question the correct answer is 6. So the correct option is B. Okay, so whenever degeneracy question is given, okay, usually what people will do, they will take a set of numbers and they'll check the possibility of those numbers and they'll find out. But you should think about other set of numbers, okay, which are possible or not. Right? This is very, very important. Right? Okay. So keep this in mind. For 51, the degeneracy is 6. Yeah, let me go to the next question. Question number 3. Yeah, students, go through this question. Question number 3. The n equal to 1 to n equal to 2 absorption frequency, n equal to 1 to n equal to 2 absorption frequency for a certain particle in a certain one-dimensional box is 6 into 10 to the power 12 second inverse. The absorption frequency for n equal to 2 to n equal to 3 is, okay, students, this is my mobile number. If you have any doubt, you can post it in the WhatsApp. You can post it in the WhatsApp, okay? Because I could not see, I could not hear your voice. So if you have any doubt, okay, just send a message to my WhatsApp number. Yeah. Okay, let me continue. See, the n equal to 1 to n equal to 2 absorption frequency for a certain particle in a certain 1D box is given. The absorption frequency for n equal to 2 to n equal to 3 is in second inverse they are asking. Okay, here frequency is given in second inverse, here also they are asking in second inverse. Right, how to do this problem? So it is given clearly, it is 1D box. Okay, particle is present in 1D box. Right, and you know very well in 1D box the gap between adjacent level delta E. Okay, gap between adjacent level gap. Okay, the gap between adjacent level is nothing but energy of the n plus 1 level minus energy of the nth level. Okay, this is higher level, this is lower level. Right, and for 1D box the energy formula is this. N plus 1, here the quantum state is n plus 1 the whole square times h square by 8 ml square minus here energy formula is n square h square by 8 ml square, because here the quantum state is n. H square by 8 ml square is common, so you can take it out, and you will get n plus 1 whole square minus n square in the bracket, and if you use a plus b whole square formula you will get this result, 2n plus 1 times h square by 8 ml square. Okay, so this is the gap between adjacent level. Okay, now for 1 to 2 transition, for n equal to 1 to n equal to 2 transition, absorption frequency is given. Okay, so what is the absorption frequency? Absorption frequency, you know very well, the gap between adjacent level is equal to h nu, the photon that is absorbed, where nu is the frequency. Right, for 1 to 2 transition, see students, here this n should be lower value, lower n value. Okay, so for n equal to 1 to n equal to 2 transition, okay, frequency is given. Now what I'm going to do, in the place of delta E I'll put this h nu. So I can write this expression as h nu is equal to 2n plus 1 times h square by 8 ml square, or you cancel h and h square here. So you'll get frequency is equal to 2n plus 1 times h by 8 ml square. Okay, this is the formula, general formula. Okay, for n equal to 1 to n equal to 1 to n equal to 2 transition, put n equal to 1 here. Okay, you will get the frequency for the transition. Right, so frequency for n equal to 1 to 2 is frequency for n equal to 1 to n equal to, if I put 1 here, I'll get 3 times h by 8 ml square. This is h. Okay, and this frequency is given, which is nothing but what's the frequency given? It is 6 into 10 to the power 12 second inverse. This value is given. Frequency for 1 to 2 transition is given, and they are asking the absorption frequency for n equal to 2 to 3. For 2 to 3, how to find the value? Okay, so frequency for 2 to 3 transition is equal to, for 2 to 3 the lower value of n is 2, substitute 2 here, so 2 into 2 4, I'll get 4 plus 1 5, so I'll get 5 times h by 8 ml square. We need to find the value of this. 3 times h by 8 ml square is 6 into 10 power 12. I'll repeat, 3 times h by 8 ml square value is 6 into 10 power 12. What about 5 times h by 8 ml square? Simple, divide this value by 3. You'll get 2 into 10 power 12 and multiply by 5. That's all. Correct? To find the value of this, okay, this value is available. To find this, what you have to do, divide this value by 3. You'll get 2 into 10 power 12 and multiply by 5. So what we'll get is 5 into 2 into 10 power 12, or 5 into 2 is 10, 10 into 10 power 12 is 10 power 13 second inverse. So this is the answer for this question. Okay, students, is this clear? Any doubt here? If you have any doubt, you can send a message in my to my WhatsApp number. Okay, and remember this formula for absorption. To find absorption frequency, right, between any adjacent level in 1D box problem, you can use this formula directly. Okay, right. So absorption frequency for 1 to 2 tranche is given, and they asked to find the absorption frequency for 2 to 3 tranche. Okay, this is the method. Yeah, let me go to the next question. Question number 4. Yeah, students, go through the question. Question number 4. The eigenvalue correspond to, yeah, question number 4. Yes, the eigenvalue correspond to the operator d square by dx square acting on the function sin x plus cos x is. Yeah, try to find the answer for this question, student. The question is we need to find the eigenvalue correspond to the operator d square by dx square acting on the function sin x plus cos x is. Okay, let me do this. So question number 4. The operator given is d square by dx square, and the function given is sin x plus cos x. Okay, so we have to differentiate this function 2 times, that's all, right? So I'll differentiate once. I'll differentiate this once. Sin x, if you differentiate, you'll get cos x. Cos x on differentiation will give minus sin x. Now I'll do differentiation second time. Cos x on differentiation gives minus sin x, and sin x on differentiation will give cos x. I can take minus 1 as common. So if I take minus 1 common, I'll get sin x plus cos x. Right? So when I apply the operator to the function, I got the same function multiplied by some constant, and that constant is nothing but eigenvalue. So eigenvalue for this problem is minus 1. Eigenvalue for the operator d square by dx square acting on this function is minus 1. So the correct option for this question is option B. Okay, take note. The derivations are quite simple. Sorry, the eigenvalue problem is somewhat simple only, but you must know how to do differentiation, right? For trigonometric functions, right? Usually they'll give trigonometric function, but sometimes hyperbolic functions may also be given. So try to learn, okay, how to differentiate if hyperbolic functions are given. Yeah, then let me go to the next question. Question number 5. The Hermite polynomial value for v equal to 2 status. V equal to 2. What is the Hermite polynomial value for v equal to 2 state? Okay, options given: 2q, 2q square minus 1, 4q square, this is actually 2, 4q square 2, and here sorry, sorry, this is just 4q square, I'm sorry, this is 4q square and this is 4q square minus 2. So we have 4 options. Okay, we need to find out the correct option. The question is Hermite polynomial value for v equal to 2 status. You know very well the general formula for Hermite polynomial. Let me write here, question number 5. Hermite polynomial. in one-dimensional simple harmonic oscillator, the wave function, okay, contains the Hermite polynomial, right? Let me write the wave function first. The wave function for vth state, vth vibrational state for a 1D box, for one-dimensional simple harmonic oscillator is we have the normalization constant 1 by square root of 2 power v into v factorial into alpha by pi whole power 1 by 4 into e power minus alpha x square by 2, then the Hermite polynomial, that is hv root of alpha into x, hv root of alpha into x. Okay, here I have given the Hermite polynomial value in terms of q. Actually q here is nothing but root of alpha into x. Here q is root of alpha into x. Okay, yeah. So how to find the Hermite polynomial value for any vth state? Okay, the formula is, general formula is this, hv of x or hv of instead of root of alpha x, I'll put q. Okay, for any vth vibrational state, how to find the Hermite polynomial? Okay, the general formula is this, minus 1 power v into e power q square into d power v by dq power v, right, into e power minus q square. This is the general formula for Hermite polynomials. Okay, yeah, this is actually a quite simple one. If you know how to differentiate functions, then you can easily do that. Now for v equal to 2 state, we need to find the Hermite polynomial. Okay, so in the place of v, I'll put 2 here. So h2 of q, we need to find the Hermite polynomial for v equal to 2 state, which is given as minus 1 power 2. Wherever v is there, you put 2, e square, and here I'll put d square by dq square into e power minus q square. Okay, minus 1 square is plus 1, plus 1 plus 1 into e power q square is e power q square. You keep this one as such. Here I have to differentiate this function 2 times. D square by dq square is there, so we have to differentiate this by 2 times. Okay, yeah, how to do that? If I differentiate once, I'll get, if I differentiate once, I'll get d by dq. I'll keep d by dq as such. If I differentiate this once, I'll get e power minus q square. If I differentiate, I'll get e power minus q square. And if I differentiate this power minus q square, I'll get minus 2q. Okay, minus 2 is constant, so you can keep it out. Minus 2 into e power q square. Okay, now I have e power minus q square and q. Right, so we have to differentiate this again. So I'm going to apply UV method. Okay, so according to UV method, first you keep this u as such, e power minus q square HS. If you differentiate q, you'll get 1. Plus, next you keep q as such, differentiate e power minus q square. If you differentiate e power minus q square, e power minus q square and differentiation will give e power minus q square, and the power, if you differentiate, you'll get minus 2q. Right, so here I have e power minus q square, here also I have e power minus q square, so you'll take e power minus e square as e power minus q square as common. Outside the bracket we have e power plus q square. If I take e power minus q square common, then I'll get e power plus q square into e power minus q square, that become 1. E power 0 is 1, so that become 1, so I'll get minus 2 times, here we have 1 and here we have minus 2q square. If I multiply by minus 2, I'll get this become minus 2 and this become plus, so I'll get 4q square minus 2. This is the answer for the Hermite polynomial of v equal to 2 state. Okay, take note. This is the value of the Hermite polynomial for v equal to 2 state. So the correct option for this question is, if you go through the option, yeah, yeah, option D. We have 4q square minus 2. Right? Take down. If you find any difficulty, you please tell me, I'll help you. This is actually a simple one. Okay, not a complicated derivation. It's a very simple one. This is the wave function for one-dimensional simple harmonic oscillator. Okay, full form of the wave function, which has a Gaussian function here. E power minus alpha s square by 2 is a Gaussian function, and we have an Hermite polynomial, and this is the normalization constant. Normalization constant also depends on V. Okay, as the vibrational state changes, normalization constant also will change. Okay, and in this I have already told you, try to remember the wave function for the ground state at least. Try to remember the wave function for the ground state. So for ground state, Hermite polynomial for the ground state is actually 1. Okay, if you calculate using this formula, you'll get the answer as 1. Right? Now I've substituted this in the wave function formula. So ground state V equal to 0. If I put V equal to 0, then the Hermite polynomial value is 1 here. Keep this function as such. Okay, this remains same for all the state. This function remains same for all the state. And for V equal to 0, if I put V equal to 0 here, 2 power 0 is 1. 0 factorial is 1. So this part become 1. So what's the wave function? The wave function for the ground state, ground vibrational state of one-dimensional simple harmonic oscillator is alpha by pi whole power 1 by 4 into e power minus alpha x square by 2. Okay, remember this function. Okay, for the ground state of one-dimensional simple harmonic oscillator. This is the wave function for the ground state of one-dimensional simple harmonic oscillator. Okay, and you know the expression for energy. Energy expression En equal to, or EV equal to V plus half times h nu. V plus half times h nu, where this half h nu correspond to 0 point energy of the molecule. Okay. Yeah. Let me go to the next question. Question number 6. Just go through the question. Question number 6. The number of peaks in the graph of one-dimensional simple harmonic oscillator for, it's not at, I'm sorry, for, okay, square of psi 4 state is square of, okay, modulus of psi 4. What is psi 4? Psi 4 means wave function for the V equal to 4 state. Wave function for the V equal to 4 state, and take the square. Right? How? If you plot this square function or the probability function with respect to x, you will get peaks. The question is number of peaks in the graph of the one-dimensional simple harmonic oscillator with the psi v square is psi 4 power 2 is. Okay. So how to find the number of peaks? Students, observe this carefully. This is actually a simple problem. See, when V equal to 0, that means the ground state. Okay, for ground state we get, if you plot one-dimensional simple harmonic oscillator wave function, right, or the probability of the wave function, the probability curve will look like this. Okay, the probability curve will look like this. You will be getting one peak if V equal to 0. Okay, this is probability psi 0 of x square. Psi 0 of x square, if you plot, you will get one peak. If you go to V equal to 1 state, okay, for V equal to 1 state, this is x value. Okay, in the plus x, this is minus x. Plus x and minus x shows displacement, and this is psi square, but V equal to 1, so psi 1 square. In the psi 1 square, if you see, you will get two peaks. There is a node at the middle, and you will get two peaks. So from this it's very clear that if V equal to 0, I will get one peak. If V equal to 1, I will get two peak. If you go to V equal to 2, you will get three peak. Then here it is given, if I plot, students observe carefully, if I plot psi 4 square, psi 4 square. So how many peaks we'll get? Okay, V value is 4 here. Therefore, if V equal to 0, I'll get 1 peak. If V equal to 1, I'll get 2 peaks. If V is equal to 4, I'll get 5 peaks. So in general, number of peaks in psi V x square plot, psi V square, right? Psi V square plot is V plus 1. So since V is 4 here, we should get 5 peaks, okay, in the graph, right? So for this question, the correct option, okay, the correct option is C. We should get 5 peaks in the graph, okay, for psi 4 square state, okay, or for the vibrational state V equal to 4, okay. Then if you find any difficulty, you can ask me. Then the next question, let me go to question number 7. Yeah. Yes, students, go through the question and try to answer it. This question we have already discussed. Anyway, just go through. If you find any difficulty, you tell me, I will help you. How to work out this problem. Question is, which among the following does not commute? Does not commute. Okay. This problem we have already discussed anyway. See, if you take the kinetic energy and L square operator, okay, they commute. They commute. You know very well, in L square we have only theta function and phi function, okay, whereas in the kinetic energy operator we have R. R will come here, okay. So the kinetic energy operator depends on R, whereas L square is independent of R. So they commute, okay. I have already told you, if one operator depends on one variable and the other operator, if it does not depend on one particular variable, okay, of the given operators, then they commute. Here, see, this is option A. What about option B? Potential energy is given clearly is a function of R and L square. Okay, see, L square is independent of R, whereas potential energy depends only on R. So in this case, they also commute. Okay. Then option C. In option C, we have Lx operator and Ly operator. Okay, students, observe carefully. Both Lx and Ly operators, if you see their formulas, Lx has sin theta and phi function. Ly also has as a theta and phi function. Okay, they are independent of R. Okay, Lx and Ly. Lx depends on theta and phi. Ly also depends on theta and phi. Therefore, they do not commute. They do not commute. Okay, and you know very well, Lx Ly operator, if you see, the value of this operator is I into H bar into Lz. This you know already. So this commutator value is 0. It is not 0. So these two operators, Lx and Ly, they do not commute. Okay. Then next one, Hamiltonian operator with L square, where potential energy is a function of R only. So it's very clear. You can write Hamiltonian into, okay, let me write here, Hamiltonian L square operator. Do they commute or not? You know very well, Hamiltonian operator can be written as kinetic energy plus potential energy, comma L square. You can separate this into two, kinetic energy, comma L square plus potential energy, comma L square. You can separate like this. Okay, you know very well, kinetic energy commute with L square, potential energy also commute with L square if potential energy depends only on R. Yes, it is given clearly, potential energy depends only on R. Therefore, this will commute, this will also commute. So it means Hamiltonian operator commutes with L square if potential energy depends only on R. Okay, so among the four, A will commute, B commute, C does not commute, and D commute. So the correct option for this is option C. Okay, yeah, remember this is very, very important. And I told you already, in the case of atoms, okay, in the case of atoms, potential energy is essentially function of R. Okay, they are spherical potentials. Okay, spherical field potentials. Whereas if we go to molecule, diatomic molecule or polyatomic molecule, in those case, potential energy not only depends on R. Okay, it also depends on theta and phi functions. Okay, therefore, potential energy is independent of R. It depends on theta and phi, so they commute. Okay, so that's why I told you in the case of molecules, angular momentum is not a good quantum number. L square, Lx, Ly, Lz, they are not good quantum numbers in the case of molecules. For atoms, they are good quantum number, because if you know any function which is eigenfunction of L square, then automatically the function will be the eigenfunction of Hamiltonian operator. So it is very simple to find the eigenfunctions of L square. If you know that, then you can find the eigenfunction for H. Okay, this is not possible in the case of molecule, right? So remember, for question number 7, okay, just go through these questions once again and check whether this is correct or not, right? So Lx and Ly, they commute, they do not commute, I'm sorry. Then students, one more information here I like to give here about Hermitian property, Hermitian operators. Remember, if two operators, okay, before that I told you, I have given all these things already. D by dx, I into d by dx, okay, d square by dx square, I into d square by dx square. Now, among these, which are all the operators? These are all operators. Which are all the operators are Hermitian, and which are all the operators are anti-Hermitian or non-Hermitian? See, d by dx is not Hermitian operator, whereas I into d by dx is Hermitian. D square by dx square is an Hermitian operator, whereas I into d square dx is not Hermitian. Okay, this for this information I have given already. Then one more information. If A operator and B operator, if A and B are Hermitian, suppose, okay, if A and B are Hermitian operators, then AB plus BA is also Hermitian, whereas AB minus BA is anti-Hermitian. It is not Hermitian, it is anti-Hermitian. It is not Hermitian. Okay, if A and B, A is Hermitian, B is Hermitian, then AB plus BA is also Hermitian operator. But AB minus BA is not Hermitian, it is anti-Hermitian operator. What about A into B? Is A into B an Hermitian operator? A into B is Hermitian. Yes, it is Hermitian only if A and B commute. Students, observe this carefully. A into B is Hermitian. Yes, only if A and B commute. Okay, so remember this information. Sometimes they'll ask questions like this. See, let me write the next page. Sometimes they'll ask question like this: Lx, Ly plus Ly, Lx. Is this operator? I'm sorry. Now the question is this operator Hermitian? Lx into Ly plus Ly into Lz. You know very well the formula for Lx is let me write the formula, minus I h bar. Okay, for Lx it is y into dou by dou z minus z into dou by dou y. Okay, and here minus I into y dou by dou z, right? This is an Hermitian operator. Similarly, minus I minus this become plus. Okay, so plus I is z into dou by dou y. If you find, both are Hermitian operators, they are Hermitian. Okay, so this combination is an Hermitian operator. So I can say the other way, simply, you need not worry about this. Remember, Lx, Ly and Lz, all these are Hermitian operators. They are Hermitian operators. So Lx and Ly are Hermitian. Therefore, AB plus BA, see, if I take this as A and this as B, then AB plus BA, this is also Hermitian. Okay, so remember this information. That's why I gave this formula. If A and B are Hermitian, then AB plus BA is also Hermitian. Right? Just for information's sake, I have given this point. Just note down. Then let me go to the next question. Question number 8. Just go through the question. The wave function n into n is normalization constant. N into r square. Question number 8. You just go through question number 8. The wave function n into r square e power minus r by 3 sin theta cos theta into sin theta into cos theta into cos phi of hydrogen atom correspond to the orbital. This correspond to which orbital? 3d z square, 3d, this is xz, xz. Let's write here. This is 3d xz and this is 3d yz. Okay, yeah, the wave function for expression is given. We need to find out this wave function expression correspond to which orbital. Okay, students, this is very easy. Always, if a wave function is given and if they ask orbital, what you have to do, first to see the exponential part. The exponential part given is e power minus r by 3. Listen, e power minus r by 3, whatever constant that is present, okay, in the denominator, okay, or below in the e power minus r by something, okay, whatever constant given, that corresponds to n quantum number. So n quantum number is 3 here. Okay, therefore this should be a 3 orbital. Okay, that is a 3 p 3 s something. Listen, and here it is given sin theta, cos theta and cos phi. You know very well the orbital x, or I'll take px. Let me give this information, student. I'll take the orbital. If you take s orbital is independent of theta and phi. Theta phi should not come, but I have theta phi functions here. Therefore, this wave function cannot be correspond to s orbital. It cannot be s orbital. Okay, for s orbital is independent of theta and phi. Okay, then for px, py and pz orbitals, for px orbital we should have sin theta cos phi. For py orbital we should have sin theta sin phi. For pz we should have cos theta. Okay, but here I don't have only 2, I have 3. See, sin theta, cos phi, 3 angular functions are there. 3 angular functions. If you have only 2 angular functions, it should be p orbitals. Okay, if you have 2 angular functions and 1 cos theta function, then they are p orbitals. But I have 3 functions, so it cannot be p orbital. It should be d. Okay, why? Because we have 3 angle functions. Whenever 3 angle functions exist, okay, then it corresponds to d orbital. Okay, and which d orbital it corresponds to? See here, suppose I'll take dx xz, I'll take xz. Why I'm taking xz, I'll tell you. For x, the function is this. For x, whenever x is there, the function should contain sin theta the function should contain sin theta cos phi, and for z the function should contain cos theta. So if you have sin theta into cos phi into cos theta, that corresponds to dxz orbital. So here it is very clear we have sin theta, cos phi. So definitely this function corresponds to 3dxz orbital. So the correct option is B. You can see, we can find the answer directly. Okay. Suppose if it is for yz orbital, how the wave function should look like for dyz. Y function, you know, y function is sin theta sin phi. So if you have sin theta sin phi, and for z the function is cos theta. So if you have this function sin theta sin phi cos theta, okay, then that orbital corresponds to 3dyz orbital. Okay, but here in our question the function given is sin theta cos phi, therefore the answer is dxz orbital. What about dxy? For dxy, okay, x is sin theta cos phi, okay, and y is sin theta sin phi, sin theta sin phi. So we have sin square theta into cos theta into sin phi. Okay, you can simplify this further. Sin square theta into cos theta, you can simplify further. So the wave function get modified. Okay, wave function get modified into a different form. Okay, let me give how it will become. I am not going to do the proper mathematics here. I'll give you the options directly. So this will give me sin square theta into sin 2 phi. For dxy orbital, students observe carefully, for dxy orbital the wave function contains sin square theta and sin 2 phi. There won't be any cos function. Okay, they may give like this, but this is the proper function, sin square theta sin 2 phi. Okay, see here sin square is there, number 2 is the order, and here we have sin power 1, so the total order is 3. For any d orbital there should be 3 angular functions. Okay, so it consists of 3 angular functions. That's the meaning, right? So keep this in mind. Then, so for dxy we will have sin 2 phi. Suppose if we go to dx square minus y square, for dx square minus y square you will be having this formula, that is sin square theta cos 2 phi. So remember, when x and y comes, then you will be having sin 2 phi cos 2 phi, like that. Okay, we can work out, but I'll just leave it to you. It's very simple only, you can find it out. Okay, for dz square orbital, students observe carefully, whenever z present alone without x, without y, okay, if z is present alone, then it should be a function of cos theta, cos square theta or cos cube theta, like that. For dz square the function is actually consists of 3 cos square theta minus 1 with some constants in front, you need not worry about that. See, you will be having cos square theta, that is very, very important. Okay, if you have whenever a wave function contains only cos theta term, it must corresponds to pure z orbitals. It may be pz orbital or it may be dz square orbital, like that. Okay, so keep this information in mind, very, very important. Next, let me go to the next question, question number 9. The Thom symbol for the ground state of boron molecule is, the Thom symbol for the ground state of boron molecule. Yes, how to find that? Listen, you know very well, for boron molecule, the B2 molecule, the electronic configuration for the molecule is ground state configuration. I'm going to write electronic configuration, sigma 1s2. Boron atom has 5 electron, boron molecule has 10 electron total. So sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and atomic number is 5. When atomic number is 7 or below 7, then pi orbital should come first, right? So pi 2 px, pi 2 py, they have same energy. Okay, so that should come first. Then you will be having sigma 2 pz. Okay, whenever atomic number is 7 or less than 7. So we have 10 electrons. I filled 8 electrons here, 2, 4, 6, 8. So we have 2 more. I'll put 1 here and 1 here. Okay, so this is the arrangement. Now these orbitals, molecular orbitals, are fully filled, and you know very well, fully filled molecular orbitals do not contribute in the term symbol, in finding term symbol. In the determination of term symbol, fully occupied orbitals do not contribute. So we should consider only this. Okay, and you know very well what is the procedure. The procedure is this: we have 2 electrons now. One electron is pi 2 px, the other electron is pi 2 py. Okay, first we should find out lambda, small lambda. Students, observe carefully. For sigma orbital or sigma star orbital, lambda value is 0. For pi orbital or pi star orbital, okay, lambda value is plus or minus 1. Okay, for delta and delta plus star orbital, the lambda value is plus or minus 2. Like that it goes. Okay, now we have 2 electrons. Both the electrons are present in degenerate pi orbitals. Remember, if you have degenerate pi orbitals, this is pi 2 px and this, let this be pi 2 py, then lambda value for one orbital is plus 1, the lambda value for other orbital is minus 1. So keep this in mind, very important. Therefore, we have 2 electrons, one in plus 1 and another one in minus 1. So lambda value for electron 1 is plus 1 and lambda value for electron 2 is minus 1. Okay, we need to find out the big lambda. I'll use the term big lambda. Big lambda is nothing but sum of these two. Okay, so lambda 1 plus lambda 2, right, which is nothing but 0. I should take only the magnitude. Only the magnitude of lambda is very important. Yes, in this case it is 0. When magnitude of lambda is 0, okay, magnitude of lambda and the symbol. If magnitude of lambda is 0, the symbol is sigma state. If magnitude of 0 is 1, then it corresponds to pi state, big pi. If it is 2, then it corresponds to del state. Like that it goes. Okay, so remember this expression. So here for boron molecule, the magnitude of big lambda is 0, so it corresponds to a sigma state. Okay, so the ground state configuration correspond to a sigma state. Now we have 2 electrons. Okay, for the ground state, okay, if you have 2 electrons in degenerate orbitals, right, according to Hund's rule of maximum multiplicity, okay, the 2 electrons should have same spin. If 2 electrons have same spin, for this plus half, for this plus half, so total spin is S is equal to 1. S is equal to, for electron 1 it is plus half, and for electron 2 also plus half, so total spin is equal to 1. S equal to 1 means multiplicity is 3. So it is a triplet state. So ground state is a triplet sigma state. It's a triplet sigma state. Then we have few more steps to go. What you have to do, see, the electrons are present in pi orbitals. Okay, remember, we need to find whether it is Jrf or un-Jrf. Okay, because the molecule is a homodiatomic molecule. For homodiatomic molecule, center of symmetry is there. Therefore, we must indicate the term symbol with whether the molecule is symmetric with respect to center of symmetry or antisymmetric. Okay, so for that purpose I am going to find Jrf and un-Jrf. Okay, students, observe this carefully. For sigma bonding molecular orbital, okay, the symmetry is Jrf. For sigma star, the symmetry is un-Jrf. Symmetry with respect to center of inversion. For pi bonding molecular orbital, it is un-Jrf. For pi star anti-bonding molecular orbital, it is Jrf. Okay, and you also know that Jrf into Jrf is Jrf. Un-Jrf into un-Jrf is also Jrf. Jrf into un-Jrf is un-Jrf. Okay, so now we have 2 electrons. One electron is present in pi bonding molecular orbital, which is un-Jrf, Another electron is also present in pi bonding molecule. This is also 1 Jrf. So for electron 1 and electron 2, the symmetry is 1 Jrf symmetry. 1 Jrf into 1 Jrf is Jrf. Therefore, the term symbol should have a Jrf symmetry. Okay, that should be placed in the right hand side bottom or in the subscript. Okay, you should place it. Okay, so triplet sigma g plus. Okay, now whenever sigma state comes, whenever sigma state exists, right, as ground state, then you must put a plus or minus sign in the right hand side superscript. Okay, plus, to find plus and minus, what we should do, we should place a mirror plane, okay, along the internuclear axis. Right, you know very well the pi 2px and pi 2p orbitals, they are perpendicular to each other. So if I place a plane in pi 2px orbital, suppose if the plane passes through the lobes, then it is symmetric with respect to the plane, therefore you will get plus 1. But the same plane is antisymmetric with respect to this. Okay, so whenever, remember, whenever two electrons, right, present in the degenerate orbitals, degenerate pi orbitals, remember, then one electron will have plus 1 symmetry, the other electron will have minus 1 symmetry. So if I multiply, I will get plus into minus is minus, therefore it is triplet sigma g minus. So this is the ground state term symbol for boron molecule. Okay, yeah, so the ground state term symbol for boron molecule is triplet sigma g minus. Okay, then let me go to the next question, because this is a very simple one, you might have heard about that. So let me go to the next question directly. Energy of the LUMO minus HOMO for 1,3 hexadiene under Huckel molecular orbital treatment is 1,3 hexadiene. Students, observe carefully. 1, 2, 3, 4, 5, 6. This is we have 6 carbon atom here. 1, 3. So the carbon number 1, 2, carbon number 3, 4, 5, 6. So in carbon number 1 we have a double bond, and in carbon number 3 we have a double bond. So 1,3 hexadiene is given. Okay, it is not butadiene, it is hexadiene, right? But you know very well, under Huckel molecular orbital treatment, okay, you need not worry about the sigma bonds. Sigma electrons do not contribute. So this is exactly same as 1,3 butadiene. Students, you need not worry about this part. Sigma electrons do not contribute. So you can treat this as 1,3 butadiene. So for 1,3 butadiene, you know very well, you know, you'll get 4 pi molecular orbitals. The energy of the lowest pi molecular orbital is alpha plus 1.618 beta. Remember the values. Remember the values. Second one, alpha plus 0.618 beta. Third one, alpha minus 0.618 beta. And fourth one, E4, alpha minus 1.618 beta. These are the energies of pi molecular orbitals according to Huckel theory. Okay. Now we have 4 pi electrons. So for the ground state, the 4 pi electrons are placed like this. Each molecular orbital can accommodate 2 electrons. So place 2 electron here and 2 electron here. So this is the HOMO level, highest occupied molecular orbital, and this is the LUMO level. Okay, and what is the energy difference? We need to find the gap, right? E LUMO minus E HOMO you need to find out. So higher value alpha minus 0.618 beta minus lower value HOMO value alpha plus 0.618 beta. Right? If you see, you will get here, you will get minus alpha minus 0.618 plus alpha minus alpha cancels, minus 0.618 minus 0.618. If we add, you will get minus 1.236 beta. This is the HOMO-LUMO gap. Okay, that is present in 1,3 hexadiene as per Huckel treatment. Okay, whether it is 1,3 butadiene or 1,3 hexadiene, you will get the same answer because the sigma electrons do not contribute. Right? So what normally people will do, by seeing this molecule hexadiene, they will simply leave the question. because they are all familiar with the butadiene. Okay, so keep this in mind, whether it is 1,3-butadiene, 1,3-hexadiene, 1,3-octadiene, whatever maybe it is. Remember, sigma electrons do not contribute. Okay, that's all. So for this question, the correct option is C. Okay, yeah. So we have discussed 10 questions today. We'll continue this in the next class. Okay, yeah. Let me turn off.